This is a tool to check whether your Haskell program will crash. So it's a nice static analysis. So I'm going to start with the kind of example that you might encounter when you're programming. Here is a function, and you've tested it once, you've decided you know what it does. So this computes the rising sequences, subsequences within a sequence. Now, you've got the chart image. Does this program crash? Is there any possible value you can give which will make this little example crash? Or alternatively, can you explain to me why this program will never crash? So, if you've seen it in the paper, please don't participate. But otherwise, does anyone have any ideas as to where it's safe, why it's unsafe, or any comments on it?
Where clause looks suspicious.
Okay, so this where clause is an incomplete pattern. There's a chance that if rise is here and turns nil, you'll get a crash at runtime. So is there some example data you can construct to get that? Or is there some proof you can construct that shows you'll never get that? Anyone like to take a guess? Yeah?
So risers will map, I hope, non-empty lists to non-empty lists.
Yes. And that is the key property. If risers takes a non-empty list, it will return a non-empty list. So because we've got this cons here, we can guarantee that we'll get a cons out, and therefore it's safe. But as you can see, it's not particularly trivial to do this, and you have the feeling that this is true, but if you tweak a definition, it will go wrong. And doing it by hand isn't very convenient. So instead, we turn it over to the Calch program, and this is the real output Calch gives. You just type Calch risers, and then Calch identifies that there's an incomplete pattern. Line 6, the where clause is potentially incomplete. But then Calch goes on to say, well, actually, the program's safe. Don't worry about that incomplete pattern because you'll never encounter it. So Calch is the associated implementation with my static checker for patterns, and it's proven the program is safe. But what's important to realize is that there aren't any annotations on this program. This is the code. There's no hint to Calch that it might want to check risers properties on non-empty list, non-empty list. So you can take unannotated Haskell code without any extensions. So what's the problem I'm trying to solve? The pattern match problem. Will your program crash? So pattern matching is one of the common ways that program will crash. So if you match against the pattern is partial, and you pass input that doesn't match the pattern, you get a crash. But you've also got the problem of calling error and calling functions like head or nil or from just or nothing. And these are all instances of the same problem. So GHC can warn you if you have a partial pattern, and in the Calch example that I showed at the beginning, GHC will warn you that indeed your pattern is partial. But Calch takes it one step further. It can certainly check that the program will crash, or tries to check that the program won't crash at runtime, even in the presence of partial patterns. So you can still have partial patterns and know that you're still safe. So how does Calch work? This is just a kind of general overview from a faraway distance. So you have a checker and a constraint language. Calch operates on a first-order core language, which we generate with YHC and first-fi defunctionalization paths, which is beyond the scope of this talk. So you then have a checker that works on a first-order core language. And this checker encodes knowledge about how the core language operates, the semantics of the core language. And the idea is that this is a reasonably exact analysis of your program. In the paper, it doesn't deal with laziness, but other than that, it's a very precise analysis. You then plug in a constraint language which talks about the types of values that an expression can take. And this is where you have your conservativeness. This is where you approximate the problem so that you can parameterize by the constraint language. And the nice thing is that there's a clear separation between the checker and the constraint language. There are only 3 operations that a constraint needs to provide to the checker, and a handful of properties to check the system. So you can easily replace the checker to get different levels of power or speed. And in the paper, there are 3 different constraint languages presented for the one checker. So when we're arguing, well, this program won't crash because we need some kind of vocabulary to talk about what kind of things we're going to be working on, what kind of things are going to be flying around the system. And Calch uses constraints, preconditions, and entailments. And as was mentioned in the beginning when we were discussing how to prove risers, we actually gave examples of all of those. So a constraint just describes a set of values. X is const constructed, Y is true, X is the infinite list. Those are the kind of values where we can say this is a set of values, potentially infinite. A precondition is a set of constraints on the arguments to a function to ensure that the function won't crash. For example, on the function head_x, the precondition is that x must be a const. And the idea is that if all the input arguments satisfy the constraints that are associated with the precondition, then you can guarantee that the function won't crash. So the precondition on risers would just be true. There is no precondition. And an entailment is a constraint on the arguments to a function to ensure that the result has a different constraint. So for example, in the risers example, we have the entailment that if you give a const constructed value to risers, you'll get a const constructed value back. And for example, if you have a const constructed value passed to null, you'll get false back. So Calch uses these three terms to talk about what functions have, what properties functions have, and try and construct a proof. So I'm just going to very briefly mention the types that are flowing around these checkers, how these are encoded, so you can get a kind of more concrete understanding of how Calch might work. So you have constraints. Constraints are opaque to the checker, but are defined by the constraint system. You have satisfaction. So does this value satisfy this constraint? And I also have a simple first-order core language data type and a proposition type doing the usual and or not type style stuff. So, how does the checker work? The idea is that you compute the preconditions to functions. Now, the hard thing about computing a precondition to a function is recursion. So, the precondition to a function, a recursive function, is very likely to be defined in terms of the precondition to that function. So you somehow need to deal with that recursion. And the way we deal with that in Calch is using a fixed point. But if you look at the precondition function here, it says, given this expression, what's the constraint required to make sure this expression doesn't crash when evaluated? And it gives it as a list of constraints on expressions, likely to be sub-expressions of the expression you start with. The problem is, if you start taking a fixed point over an arbitrary expression, a recursive expression, it's very likely that you'll get an infinite expression being constructed. So you'll never reach the fixed point. So to solve that, we have reduce, the second thing. The idea is you can take a constraint on an expression, so I'm demanding that this big expression is a const, and translate it to a proposition of constraints only on argument positions, or you can think of it as on the free variables. So given this big expression has this constraint, you can then identify what the constraints are on each of the free variables within it. And that's in a way that's conservative, so that the constraints on the free variables will ensure that the constraint holds on the whole expression. And that's what we use reduction for. So we reduce a proposition of constraints on expressions to a proposition of constraints on arguments. And once you've done this, a proposition of constraints on arguments, free variables, there are a finite number of free variables in the term, so you can start to see how that's slightly more practical to find a fixed point over it. And after we've got mechanisms for computing the precondition of something and for reducing something, we can fling both of these through a fixed point, find the fixed point of the precondition, and then if the precondition on main is true, the program won't crash. So this is the only kind of actual code, real bit of the checker I want to show you. But I hope you can see that the actual way of computing the precondition is fairly simple. It's a fairly simple structural analysis on the type of the data, on the data type. So for example, the precondition on a variable is true. Just evaluating a variable won't crash if you're working in a strict language. if you evaluate a constructor with some arguments, then all the arguments better not crash. If you evaluate a function call with some arguments, then you have the constraint that all the arguments must not crash. And if you get the precondition of the function and substitute in variables, then that must be safe as well. As you can see at the top, precondition is defined by just reducing pre. This is the kind of the interesting case. If you have a case expression, so if you have case error of, then that will crash. So precondition needs to say no, false. So the scrutiny must be safe. And for each alternative, either you don't take the alternative, or if you do take the alternative, it's safe. And that's captured by this. So if the scrutiny is not a member of the constructor or an alternative, that's safe. Or the right-hand side of the alternative could be safe. And either way, you're going to get safe program. And in this thing, you'll notice I've used one operator, this weird kind of membership with a pointy membership operator. And this says, is this expression constructed by one of these constructors? So I've used it here. Is the scrutiny constructed by one of the constructors that isn't the one you're at the alternative for? So you can see, now I'm talking about constraints, so that's the kind of interface of constraint. Reduction is implemented in a very similar way. It's in the paper, and that does what I said earlier. And that requires all three of the constraint operators. But there are only three constraint operators, so it's not too hard. And in both cases, you just take a fixed point and continue on your way. So, now I'm going to talk about the constraint operators. So you've got this checker parameterized by these three operators in this constraint data type. And then you need to call these operators to manage the constraints and to operate over the constraints in an abstract way. So you provide three operators for a constraint language, and one of the important things is that none of them are dependent on the expression type. So the checker deals with expressions, and the constraint deals with values. So the simplest is the membership that was in the precondition. So given some value, alpha, and a set of constructors, this constructs the constraint saying this value must have one of these constructors. So one possible implementation, if you want to say x is a cons, you can kind of think of building up a set of possible pattern matches. So, and one of the ways to do that would be say x is in the set of patterns, well, underscore cons underscore. You also need to provide a zooming out and a zooming in operator on constraints. So the idea is you can move forward down constraints and backwards up constraints as the program requires. So given a value, an expression A, which you said, I must be cons earlier, you now want to wrap the value A with a just to make a just A. At the same time, you want to wrap the constraint cons with a just, so that you've still got the same constraint for the same value. And that's done just with this zooming out operator. So given a cons, if you've got the pattern cons, and you're wrapping a just around the value that has the pattern cons, you now have the pattern just cons. And similarly, there's a zooming in on constraints operator. So if you have just A being just the cons, you then want to see, well, if I have a just constructor at the front, what are the constraints that I have on the fields to the expression? And that's what this introduces. You then have some properties on constraints. So constraints must be internally consistent. If you say, I want this value to be a cons, and then you say, I found out this value is a nil, then it must be false. And you also must have a finite number of constraints for any given type, so that you can guarantee termination. So in the paper, there are three constraint systems. I'm going to talk about the NP constraints here, because that's the one I found in practice was most useful. So the idea, when you're representing information about a value, you want to represent a finite amount of information about the value, but you want it to cover as many possible values as you can. So you want to talk about infinite lists, but in a finite way. So the way NP constraints work is you have information about the constructor at the root, and you have information about the constructors ever after. So given this kind of list, you can constrain this value, and you constrain all these four values with only one expression. So I can say all these tail values are cons. I can say they're all nil, i.e. there's only one and it's nil, or I can say they're unconstrained. And similarly for the values inside the list, I can say something about the head of the list, and I can say something about every element thereafter. So I can't have any precision to say that the second and third elements of the list are different. And that ensures that we have a finite number of constraints for a given type. So I'm just going to skip through this a bit quickly. So here are some examples of NP constraints. So to say something is a cons, you would say its first head element is a cons, and its actual element is unrestricted, and the tail is made up of nils and conses which have unrestricted fields. So for something like map head, you can express the property as either the list is a nil, or a cons whose first element is a cons. This is talking about the inner list. And then recursively, it's just the same. So you restrain every element within the list to be a cons. So I ran the Calch tool on the NoFit benchmark suite, and it's kind of an interesting comparison to run it on the NoFit benchmark suite because they're not real programs that real users use. So they do crash in certain circumstances. One of the programs, if you don't give a perfectly valid regular expression, it will crash. But that doesn't matter because they're mainly used for benchmarks. So one of the few things you can take away from the NoFit benchmark suite, I think, is the time. Calch takes around 1 to 2 seconds on most examples in the imaginary section of the NoFit suite, and up to 8 seconds in one example. So we're not talking a very cheap check, but we're not talking outrageously expensive either. So I want to talk a bit more about the HS Color program, which is the one big case study I did with Calch. HS Color takes a Haskell source program and prints out a colorized version either to the console, to HTML with CSS, or to LaTeX. It's 5 years old, it's had 6 people contributing patches, and there are 12 modules, 800 lines of code roughly, not including all the libraries like Prelude, List, System.io. So it's a real project that people really use on a day-to-day basis. So it's the kind of thing you hope wouldn't crash. And you might really hope it doesn't crash. It's actually used online on the website. So you can go to hpaste.org, paste in your Haskell snippet, and it will run it on the server and generate you the HS Color result. So if it crashed and it was a C program, we'd be talking buffer overflow exploit on the server. Because it's Haskell, about the best you'll manage to persuade your Haskell program to do is print out an annoying error message. So it's a real program with real users, so I thought, let me check that it doesn't ever crash with a pattern match error. But it does. So the first thing I found is that if you have, the way it stores its preference file is just using read and show. So it takes the pref structure and shows it and writes it to a file, and then it reads it from the file, reads a buffer from disk and calls read on it. Just read, not reads or anything. So if the user modifies the file, the program may crash, and in fact, if the pref structure ever changes in HS Color, then it will also crash. So Calch identified this bug and fixed it. But it's interesting to see what Calch does and how Calch tells you there's a bug and where Calch tells you there's a bug. So you run Calch on HS Color, which is the root module, which imports all the other modules, and it says, check prelude.read no paths. It's identified the error message you might get if you ran the program. And it's now going to check that that error doesn't occur. So it goes, well, I've noticed that the Prelude's version of read is partial. So you think, okay, I know Prelude's read was partial, that's okay. I now noticed that language.haskell.hscolor.colorized.parseColorCrafts is also partial. And that's the point where you think, oh dear. Obviously, that function is calling read in an unsafe way. So you can go straight to that piece of code, look at it, see what it does, and fix up the bug to use reads. And it then propagates the information all the way up to the main piece of the program, so you can see almost a stack trace that would be generated if your program crashed. So then I continued running after I fixed that bug, and I found another bug. The latex output mode has this, so it calls init on x's, and x's isn't necessarily a non-empty list. And it turns out if you actually put the file single quote and call hscolor-latex, it'll crash. So that got fixed. And there's a very, very similar bug with the HTML anchor output, but this is the one that hpaste actually uses. So this was a way to crash hpaste for a while. Open bracket, tick, close bracket. So that was fixed. And then there was a fourth issue. One of the problems with static checkers is it may throw up false positives. So it may say there's a problem here, but there's actually not. And in all of hscolor, they found 4 issues, 3 of which were real crashable bugs, and the 4th one wasn't. However, it did turn out that this was a nice refactoring and the code should probably be written this way in the first place. I actually went through and proved why this particular case couldn't be reached as a crash, and it required the fact that the length of common lexeme in Haskell is at least 2 characters long. So it's a fairly fragile proof, it's fairly distributed throughout the whole program, but this was the only one that Calch couldn't come up with on its own. So the end result is that hscolor cannot crash, and Calch has checked it cannot crash when I checked it, which was a few months ago. And that requires only 2.1 seconds of computation time to check the entire program. And 2.7 megabytes per moment. But I also looked at some older stuff, like the finite map library. And this actually turns out to have an inexhaustive pattern as well. It has 14 non-exhaustive patterns, 13 of which Calch can say is safe, and one of which it says, oh dear, it might not be safe. And this is the one, and it turns out it's really not safe, and you can crash the finite map library, admittedly with a fairly strange instance declaration. I also tried it on Xmonad. No bugs were found, partly because Xmonad had a lot of very good testing, and the code is fairly simple, fairly short and well reviewed. But it did make some explicit assumptions visible, and I think it helped them. So there are a few alternatives to check. You can use dependent types or a contract language like Epigram or Haskell. And you can also do the small check thing. In reality, often bugs are simple. So small check will typically find the kind of bugs that Calch will find. Although small check gives you a check that it didn't find anything. It doesn't, the absence of nothing. By not finding anything, small check doesn't say there isn't anything to find. Whereas Calch does say there really is no problem with this program. So, in conclusion, I think pattern matching has actually been overlooked in functional programming. It's something we use all day long, and the Darks project had 13 bugs in their bug tracker are from just errors. So this is real source code tracker. Someone's run it, and it's gone from just nothing. And they've probably sat down and wept. And there are 19 pattern match errors as well. So, over 30 cases where their program was incomplete, and they found out when a user ran into it. So Calch is a nice analysis. It's got several different constraint models, so you can hopefully plug in one that's appropriate to your task, and there's certainly scope for looking into different constraints to see which ones work well. And I think Calch is a good step towards a solution, and it's already found some real bugs in some real programs that actually have real users. Thank you very much.
Do we have any questions? Please come up the mic.
Thanks for a great presentation. So I would like to ask you, can you characterize the cases in which Calch doesn't work?
Well, the checker is pretty much complete other than laziness. So if it's, as long as it's not an issue that's because of laziness, then it will be characterized by where the constraint doesn't have power to represent something. So with the MP constraints, it's if the property was, so if you need to say a list is length 2, it can't represent that. If you need to say the list is length 0, 1, or infinite, it can. So it's all based on the constraint language. And yes, you can characterize it by looking at the constraint language.
Along the same lines, do you think it would be easy to adapt Calch to a default strict language?
I think Calch may already be adapted to a default strict language. It turns out the only cases you really have laziness guarding pattern matches is things like and or, because people use them like the C and or. And if you inline those at the beginning of the checker, then it's almost no difference between raising and stretching.
Any other questions?
Yes. Can you do a modular analysis, or is it whole program only?
At the moment, it's whole program. If you wanted to, the nice thing about it is it computes the entailments and in the entailments it needs, rather than all possible entailments. So if you were to go modular, you might want it to pre-compute as many possible entailments as it could come up with, which would probably slow it down.
So,
Here.
can DXC crash?
I have cool, yes. GXC is pretty big. It's a lot bigger than any of the examples I've tried it on, but the reason I haven't tried it on larger examples is because I can't let them go through YXC. So it's possible that you can try it on GXC, but maybe a few years off.
The GXC is also higher order, right?
Yeah, but the defunctionalization works pretty well. That doesn't turn out to be the big problem, usually.
So, if there's a JDT or a little bit fancier data type, do you approximate that into a regular array?
Well, it works on an untyped core language, so it actually doesn't need to. If the elaboration removes cases that can't be matched with JDT properties, then Calch can work with that extra knowledge and eliminate it, or never even consider there being an error there. So it should work quite well with JDTs, but the core language that we use doesn't have that.
You said it works on an untyped core language. How does your approach compare with using a data flow analysis to see what kind of constructors can flow into a case pattern?
It's certainly related. If it was higher order, it would be a lot more like a data flow analysis. But because I do a step before that eliminates the higher orderness, then it becomes a lot simpler, and the data does flow, but the data only flows in the fixed point.
Okay. Well, let's thank our speaker.